Then I do the share screen again. And I'm going to go back again. Helicity is defined as the projection of the direction of the spin on the direction of momentum. This is the definition of helicity. Okay? The thing is that helicity is not a Lorentz invariant. That means that two observers would not necessarily, when measure the helicity, they're not going to measure necessarily the same value of the helicity, and I gave you a heuristic explanation of why this is the case. Okay? If the particle travels at the speed of light, then helicity is conserved. But this is a specific case, this is not the general case. All right? Okay, so today's main topic, I'm actually going to, it's defined as a tutorial. You haven't gotten a tutorial last time, but you will get a tutorial today. It's a subject that we will discuss, I think, even further, but we should start discussing it now. This is about discrete symmetries. But even before I'm going to do that, I want to mention just in a word, as you have seen, I had some time to look at your exercises 1 and 2. Not yet at 3 and 4, this will be done in the coming days. And there was one point that jumped to my eyes because I thought this is something which is kind of trivial, but it wasn't so much. So in the first problem set, in section question number 1, 3, you were asked to say what is the wavelength of a particle that has a momentum of 1 GeV. And I wrote explicitly, write this in ordinary units, which means meters or centimeters or something like that. Now, I didn't think it's going to be particularly difficult, and especially because we derived in class, or at least I showed you in class, right, that H bar C is 0.2 GeV times femtometer. So, and what we know is that X, right, is just 2 pi H bar, right? So X, right, is just 2 pi H bar C divided by H bar C, which is 1 GeV, divided by 1 GeV, sorry, this is the momentum, divided by 1 GeV, which is the momentum. Right, so just 2 pi times 0.2 GeV femtometers divided by 1 GeV, so just 1.3 femtometer. For some reason, some of you got confused there. I'm not sure why. Something easy to remember, right? 1 GeV. For me, the way to remember it, right, 1 GeV is the mass of the proton, roughly. Right? About 1 GeV is the mass of the proton, and 1 femtometer is the size of the kernel of the atom. Okay, so this was just one quick comment. I didn't see anything in particular that jumped into my eyes in most of your questions, most of the other problem sets that you handed up. Okay, so today's subject is discrete symmetries. It's a tutorial, but it's a long tutorial. So the background is the following, right? We like symmetries in physics, right? We like symmetries, not because just they're beautiful and nice and handy, but in physics, a major part of that originates back to Netter's theorem. I don't know if you've seen that. Netter's is Amy Netter, right? Netter's theorem. It states that with every symmetry, there is a conservation law. There is an associated conservation law. Right? To any symmetry, There's an associated conservation law. Normally, which one of you have seen the proof of Netter's theorem? One that I can see. Okay, it's something which we prove. It's not that the proof is not very hard actually. I might prove it down the line at a certain point. This is one of the basics of quantum field theory, and in one of the first lectures there. You know, for example, the laws of symmetries are symmetric with respect to translation in time. That is a sophisticated way of saying that the laws of physics today are the same as the laws of physics yesterday. They haven't changed, right? The laws of physics are the same. And the conservation relation that is related to that is conservation of energy. And Netter's theorem actually shows that, right? The fact that we have a symmetry in time means that energy is conserved, right? Symmetry in translation means that linear momentum is conserved. But what is a symmetry? I haven't defined a symmetry yet. So a symmetry really is an operation. Symmetry. This is an operation that one can perform on a system that leaves it invariant. Invariant means that the new configuration after I made the operation is identical to the original configuration, right? Right. So, you know, for example, you know, take a equilateral, I think it's called, right? Equilateral triangle. Right. This is my triangle. 1, 1, 2, 1, 2, 3. Right. Now I rotate it. So I make an operation where I rotate it by 120 degrees. And I end up, right, with the same triangle rotated, right? I mark with lines the sides, but if you look at the system, if they're identical, right, you cannot tell that anything happened. So that's called a symmetry. Of course, if I rotate it by not by 120 or integer multiplicities of 120 degrees, then I don't get a symmetry. If I rotate it by 60 degrees, it's not a symmetry, because then I will end up with a triangle that looks like that. So this is a symmetry. Right? I did something, but you cannot tell, because it hasn't changed. Now, we speak in physics about two types of symmetries. We speak about continuous symmetries, right, such as rotations, right? That means that they can occur in infinitesimally small angles, right? Rotations or boosts or things like that. And there is another type of symmetries, which is discrete symmetries, right? I can look at the mirror, this is a symmetry. Okay, so we speak about continuous versus discrete symmetries. Or I can do time reversal. I can take a movie and I can play it back in time. Right? I can take a movie of, you know, 2 billiard balls colliding and going in some 2 different directions. And then I can take this movie and play it backward in time. And if it's just 2 billiard balls, you couldn't tell. that I'm playing it backward in time. If it's a glass that is broken, then you see that I take the debris suddenly mixes up, and you say, oh, that cannot be. This is happening backward in time, but that's because that violates the second law of thermodynamics. You see that entropy starts growing, and you say this doesn't make sense. Okay, so today I want to speak about two such discrete symmetries. One is called the parity, and one is called charge conjugation. So let's speak about parity first. It's called P. That's an operation. So this is a discrete transformation that acts to inverse the spatial coordinates. So this is a discrete transformation that acts on the coordinates. When it works on the coordinate r, it changes it to minus r. So if I have a right-handed coordinate system, and I look on a parity, then it becomes a left-handed coordinate system. Now note that I cannot get the parity, I cannot get this transformation by any combination of rotations and boosts. It's standalone. So now let's say that we have a system that is described by states psi. So consider system or particle, right? Described by psi. Now, if I apply two consecutive parity transformations, what's going to happen to the system? What's going to happen to the system if I do two consecutive parity transformations?
It'll stay exactly the same.
It'll stay exactly the same, right? So if I act on the system with p squared psi, right? I'm going to call the eigenvalue of p eta. So it will be eta psi squared psi, and this is going to be equal to psi. So I deduce that when I act once on p, right, has to be plus minus eta psi, which is plus minus psi, plus minus 1 psi. In other words, what I just show here is that the possible eigenvalues of the operator P on a given state are plus minus 1. So the possible of the operator P. Is there anybody here that is not familiar with these basic concepts of quantum mechanics, eigenvalues, etc.? Is there anybody like that here? No. Okay, I'm glad. So on the operator P, or eta psi plus minus 1. Now, generally, when we speak of a wave function, we have two parts. There is an intrinsic part, right? And there is an intrinsic part, the spin, right? The flavor, the color, and there is a spatial part of the wave function, right? Radial and angular parts. So for many systems that we're interested in, we have these two separation. So let's write it down, but it's important. So generally, the wave function is composed of an intrinsic part and spatial part. This is the spin, right? Flavor, color, right? Spatial part is the radial and angular. Now, for many systems or many particles that we're interested in, right, we can take the spatial part and write it in terms of spherical harmonics. Now, who here did not see spherical harmonics? Let me see. Nobody is raising their hands. Okay, so we can write down often, right? Not always. Write down. Well, we can always do that. It's not often useful. We can often write down. Often write this the spatial part in terms of spherical harmonics. Right, psi lm or just some function of radial function part times ylm of theta and phi. Right. Now, when we apply the parity operator, right, P that acts on R, what does it do? What happens to R? Just the radial part. Think of it, I have a vector. Now I change the coordinates. What will happen to the vector? Just rotate, right? I just change the coordinates, right? So what happens to the radial part of the vector?
Nothing.
Nothing, right? R goes to R. What happens to theta? Right, remember, this is theta. What happens to theta now?
Both theta and yes.
Right. What happens to phi? It goes to phi plus phi. So under parity, what we get, that parity acting on the YLM, theta and phi, give us YLM of pi minus theta and pi plus phi, which, if you're familiar with the YLM, this is just minus 1 to the power L times YLM of theta and phi. Okay, just open the YLMs. So this is, of course, not the all of it, because this is just on the spatial part. So if we take the parity transformation on a given state, then it can act on both the spatial part and the intrinsic part, right? That's because the fundamental particles, right, do have intrinsic structure, if you want, or intrinsic parity, right, such as spin, although we often treat them as point-like particles, right? So overall, right, and when P acts on the, when P acts on a state, one must consider, right, state means a particle, right? One must consider those the spatial part and intrinsic part. Right, this eigenvalue is theta. So overall, P acts on psi lm of R is equal to eta phi times minus 1 to the power L times psi lm. So a few comments now in place on what we're doing. So the time, of course, is not affected by parity transformation. Now, by convention, it's really a convention. It's useful now. Convention. Convention is also T. By convention, so the intrinsic part of spin half fermions is defined as +1. For anti-fermions, it's a -1. So, for example, right, the intrinsic part of the electron, muon, neutrino and quark are all +1. But for the positron, anti-neutrino and anti-quark, this is -1. Very similar to what we had in the initial definitions of the electromagnetic charge. Now, parity is a multiplicative quantum number. So if we have a system which contains two particles, parity is a multiplicative quantum number. Right, so P, psi, A, and B, right, would just be intrinsic parity of A, intrinsic parity of B, -1 to the power L. L is the relative orbital angular momentum between them, and then psi. Now, okay, what else? Conservation of parity means that it commutes with the Hamiltonian, right? Conservation of parity is really the reason why we're saying all that, because that's what we're going to use to solve problems, right? Conservation of parity means that the parity commutes with the Hamiltonian. And that means that applying the parity transformation to the initial and final states give the same result. So that's the meaning of conservation. And another very important consequence, I think I mentioned that already in last week's lecture, is that the parity is conserved in the strong and electromagnetic interactions, but it is not conserved in the weak interactions. I discovered that. I told you got Nobel Prize for that. Okay, questions about that? So, no questions? So one guy just disappeared for some reason. Very strange. What happened here?
I have a question.
Yeah.
So if we flip R to minus R,
yeah,
and rotate all the angles accordingly,
yeah,
that kind of sets out a specific special point in space-time, right? So it doesn't really work with Lorentz invariance anyways.
This is just a transformation. It's not the Lorentz transformation, it's a different transformation. Right?
Yeah, but it presupposes a special point in space.
Well, it is at it is at the point of the particle, right? Where the particle is located. Okay, go on. Maybe I'm not sure that I fully understand.
So if I have like an interaction between particles,
yeah,
then there's some separation between them. Which point do I choose to have my transformation?
Exactly.
Rotate about.
Exactly at the point. Well, okay. The important point here is what is written down here. The parity transformation. Well, I said that the parity is a symmetry. And I said that the parity is conserved in strong and electromagnetic interactions, but not in electroweak interactions. That is the important part here, because that means when we have an interaction, then the parity of the state, right? It's like when I speak of a state, you just ask about interaction between particles, right? So I can treat the initial state, remember, in a basic sense, the wave functions extend over the entire space, right? So I make a parity transformation, I switch the entire space. But what's the important thing for me is what I just highlighted in red here, that the initial and final states, applying the parity to the initial and final states give the same result, which means that some interactions are occurring in nature and some are not occurring in nature because they do not conserve parity. So going back to your question, I mean, the wave functions are defined over all space. And so the parity is just reversing the space, essentially. The coordinates are, I guess, are not really essential here, right? You can, I mean, the choice of the center of coordinates where you do the transformation is not really essential, right? Because if let's do a parity in 2 dimensions so I can plot it, right? So if I have a vector here, right, I do a parity transformation. The vector is now here. Now it's not really a vector, it's a wrong description because it's a wave function that extends over the entire space.
But in this case, you did, if I took away the axes, how would you know where to put it? It's frame dependent.
I don't care. What I care about is the symmetry here. I don't care. What I care about is that there is a symmetry, that the parity would be conserved or not conserved. Right? What I care about is to see whether a given interaction can take place in nature or not. Right? If I were to choose okay, let's just do an example, and hopefully this will clarify things. And if not, then we'll discuss that afterwards. It's a little bit of a lengthy example, but I think it's a good one. Well, if you're familiar with the background of angular momentum. So we want to determine. Question. Example. Question. Determine the intrinsic parity of the negatively charged pion based on the experimental fact or observed fact that or observed reaction, not observed fact, right now, observed reaction of a pion capture by deuterium D plus pion minus goes to 2 neutrons. D plus. What am I doing? This is the deuterium, the kernel of the helium, of the 2 known as H2. This is the deuterium. And we're seeing this reaction, right? Pion capture by deuterium. So I'll give you some parts of information that we're going to have to use in order to determine that. So the deuterium really is a bound state of a proton plus a neutron. So D is a bound state of P plus N. D is a kernel of hydrogen atom with an extra neutron. The relative angular momentum is 0. The total angular momentum of the deuterium is 1. And for the pion, J pion, it's a 0. Now, experimentally, the way this capture is being done is called an S wave. It's shear wave or elastic wave. So the relative orbital angular momentum between them is 0. And the last thing we know is that this reaction occurs via the strong interaction, so parity is conserved. So in order to answer this question, we're going to make use of a lot of information. Again, I hope you've seen that. That's going to be parity conservation, angular momentum conservation, and the selection rules for the addition of angular momentum, and the symmetries, of course, under interchange of indistinguishable particles. The 2 neutrons are indistinguishable. So how are we going to solve that? Anybody have any idea? So let's start by denoting the initial and final orbit states of the orbital angular momentum by Li and Lf. Li and Lf. Are the initial and final states of the orbital angular momentum. Start with that. So we know parity is conserved. So parity of the deuterium plus the pion is equal to the parity of the 2 neutrons. Now, this parity is just I said intrinsic parity, so eta deuterium eta pion times -1 to the power Li, right, is eta neutron times -1 to the power Lf. Right. Now Li, right, the initial orbital angular momentum is just the angular momentum of the deuterium, which I said is LB equal to 0, plus the relative orbital angular momentum, which I also stated this is 0. That's kind of easy. And the intrinsic angular momentum of the neutrons, I don't know what it is. I know it can be either -1 or 1, but I have eta n squared, which I know must be a +1. So overall, we end up with eta deuterium eta pion is -1 to the power Lf, the final orbital angular momentum. Okay, you with me? Questions? Okay, so in order to proceed, we want to get the intrinsic parity of the pion. So that's so eta pion. That's what we're after. So we still need to determine that. That's the next step is to determine the intrinsic parity of the deuterium, eta d. Now we know that parity is multiplicative. Right. So we know that eta deuterium is eta neutron, eta proton times -1 to the power LD. So eta neutron, eta proton, actually they are 1, or that will be the same anyway. So it's a 1 times 1 times -1. And LD, I actually wrote it down, is 0. So this is 1. So it means that eta pion is -1 to the power L final. So now we just need to find out what is L final, the orbital angular momentum of the final state. So remain to find LF. Okay, for that, we need to be we need to look at conservation of angular momentum. Now, again, I'm not sure if you've seen that. Okay, since it's reasonably simple, so I think I shouldn't be afraid of just doing it. So we said that the relative orbital angular momentum between the deuterium and the pion is 0, right? We said that, so C1, we said that I is equal to 0. And that the initial orbital momentum is also 0. So the total angular momentum in the initial state okay. So that means that the I didn't say that actually. Okay. So the total angular momentum this means the orbital plus spin. the total angular momentum, right, Ji is J deuterium plus J pion. Right, by the spin is, let's say, this is 1. Did I not say that? Actually, I did say that. Okay. Let's see. Okay, JD is equal to 1, J pion is 0, and the relative angular momentum between them is also 0. So that's fine. So J, I didn't need to say that. JD plus J pion is 1. And so conservation of angular momentum is that J final is also 1. Now J, remember, is the orbital angular momentum plus the spin. So in order to proceed, I have to resolve to addition of angular momentum. So we know that JF must be in the range of LF minus SF or LF plus SF. Have you studied addition of angular momentum? Who have not studied addition of angular momentum? Please raise your hand if you have not studied, if you have not seen this before. But nobody is raising their hands. So I will assume that you have seen that, which is quite good. What is the spin of the neutron? I think we kind of mentioned that. What is the spin of the neutron?
1/2.
1/2, right? It's made of 3 quarks, right? D, and U. Each one is 1/2. But so in principle, it could be 3/2, but then it would be called a different particle. That's a delta particle. So ddu with S equal 3/2 is delta. So the 2 neutrons, what's their spin can be? What's the total spin of the 2 neutrons?
1.
Well, it can be either 0 or 1, right? It can be like that or like that. Right? So it can be either 0 or 1. We're not sure at the moment which they are. So the options we have for the final states, right? So options for the final states, psi and n, right? So it can be, we know that J final is 1. S final can be 1, right? But in that case, L final can be either 0 or 2. But it can be 1 as well, right? So JF is equal to 1, SF is equal to 1, LF is equal to 1. Or JF is equal to 1, SF is equal to 0, in which case LF has to be equal to 1. We have 3 options for the neutrons in the final state. Now the question is, which one is the correct one? So here we have to resort to the symmetry properties under exchange of particles in order to choose the correct wave function, the correct state at the end. And we use symmetry properties. So, what do I mean by symmetry properties? Right, we have two neutrons. Which type of particles are they? Which type of particles are the neutrons?
What do you mean by type?
Well, I mean fermions, not bosons, right? So neutrons are fermions. What do we know about fermions? What do we know about fermions? That they obey the Pauli exclusion principle, right? Right? Which means that this total wave function, right, psi and n of the two neutron system, what do we know about it? If the particles obey the Pauli exclusion principle?
Antisymmetric for exchange.
Two people spoke at the same time, so can you please try again? It is anti-symmetric, right? I guess that's what we want to say, right? So the total wave function is anti-symmetric with respect particle exchange. So question now is which of the three options we have give us anti-symmetric wave function. So let's see, for the spin part, so three options, 1, 2, and 3. Which one is anti-symmetric? Well, we can guess or we can calculate. I prefer the second one. So calculate, right? Let's look about the spin. So we have spin, we have two parts, right? The wave functions has two parts, right? Spin and L, orbital angular momentum. Let's look at the spin. So S equal to 0, right? You can think of it as a 0, 0. Right? It should be proportional to what? Spin up, spin down, plus or minus, sorry. Spin down, spin up. This is of course anti-symmetric. And if S is equal to 1, then again we have, this is total S, right? So S and SC, right? We have a 1, 1, 1, 0, and 1, minus 1. So this will be up and up. This will be down and down. This will be up, down, plus down, up. So in all cases, this is symmetric. This is for the spin part, right? What about the angular orbital part? So this or spatial part. So that's kind of related to the question I was asked previously about that. So if I'm exchanging the two particles, it's really equivalent to applying a parity transformation, right? So exchanging the two particles is equivalent to applying a parity transformation. Right? When I apply a parity transformation, that the eigenvalue under the exchange is -1 to the power L. Which means that states with even L are going to be symmetric and states with odd L are going to be anti-symmetric. So even L, yeah, it's going to be symmetric, that's fine. So now we can merge these together. Right, so let's look at this spin state, the spatial state. I'm going to say, okay, the three options I have here. Oh, I love this technology. Let's see. So the first one, SF is equal to 1. This is symmetric. And LF is 0 to 2. So this is also symmetric. So I have a symmetric times a symmetric. 1 gives me symmetric times symmetric. It's symmetric. Second option, S equal to 1, that's a symmetric, times L equal to 1. L equal to 1 is anti-symmetric. That's anti-symmetric. And the last option is S equal to 0, which is anti-symmetric, times L equal to 1, which is anti-symmetric. That is a symmetric. So the only combination which gives us an anti-symmetric wave function is S equal to 1 and L equal to 1. So only combination that gives anti-symmetric wave function, right, that can describe the two fermions, the two neutrons, right, is SF equal 1 and LF equal 1. So we conclude that the orbital momentum in the final state, it must be LF equal to 1. And going backwards to what we derived previously, that means that the intrinsic parity of the pion, so eta pion must be -1 to the power LF, which is -1, is negative. Cool, isn't it? Okay, it was a little bit technical, and what I'm a little bit more concerned is that it made use of additions of angular momentum. It's not very difficult, but if you're not familiar with that, it can be a little bit confusing. So I want you to make sure, go over it at home and make sure that, that things are clear in your mind of what I did here. That you don't really get lost, or not more than actually needed to get lost. Questions? Now, did I give a proper answer to the question about the choice of coordinates, which I do the parity? You see that it doesn't really matter. Okay, let's proceed. I knew it's going to be long. Now I'm afraid I won't be able to finish this part, this tutorial today. In which case, I won't give you the next problem set today, but I'll wait until I'll finish that on Thursday, and I'll give it to you on Thursday. But let's continue. I told you I want to discuss two symmetries. So one was the parity, and the second one is a charge conjugation. So C stands for charge conjugation. So basically, a charge conjugation is an operator that turns a particle into an antiparticle, and vice versa, of course. Right? So C turns a particle into an antiparticle, and vice versa. Right, so C that acts on the proton gives me an antiproton. C that acts on the electron gives me a positron. So under C, all the intrinsic additive quantum numbers change sign. So it's not just the electromagnetic charge. It's the lepton number, it's the baryon number, it's everything. But under C, operator, it's important because, you know, sometimes people forget that, you know, antiparticle is not just the opposite electromagnetic charge, it's the opposite of all charges. Under C operator, all intrinsic additive quantum numbers change sign. So if we generally denote all the quantum numbers by Q, right? So C, let's call it Q. So C that acts on a state psi, that gives anti-psi, psi Q T, going to psi of minus Q R. And C does not change the spatial or time coordinates. So only for particles for which Q is equal to 0, right, such as the photon or the pi 0, right, the zero charge pions, or for states that are composed of particle and antiparticle, right? We have a pair of electron and positron, or a quark and antiquark. These are eigenstates of C. Right? So eigenstates of C, only states for which Q is equal to 0, such as photon pi 0, or particle plus antiparticle, is E minus plus 4 plus anti-4, etc. Now again, a few comments. So unlike P, the space and time are not affected by this transformation, right? So variables that depend on the space and time, momentum, spin, etc., they do not change sign under C. Space, time, is not affected by C. So variables such as momentum, spin are unchanged. Again, similar to P, if I apply C twice, what do we get? What do we get when we apply C twice? Yeah, lost all of you, right?
You're back now. We are back. You're back. Everyone's back.
Everyone, I don't know. So what happens when I apply C twice?
Nothing.
Nothing. I go back to the original state. It's not nothing. So what's the eigenvalues of C?
Plus minus 1 again?
Yeah, very good. So applying C twice brings back the original state. So eigenvalues of C plus minus 1. Okay, take a step back because I feel that I lost half of you at least. A particle is a state, right? Now, the whole idea why I'm bothering with this, I go back to what I said at the beginning of this lecture, right? We love symmetries in physics because symmetries are associated with conserved quantities. In particle physics, right, a symmetry, as we just showed in the example, can tell us whether a process can occur or cannot occur. There are processes that do not violate any of the other conserved quantities that we spoke about, lepton family, charge, etc., and they still do not occur in nature because they do violate parity or charge conjugation or something of that kind, right? So we use these symmetries to determine whether some processes can take place or not. Okay? Now this is a symmetry, meaning that if I do something, right? Doing a charge, that means that I'm taking all the particles, transforming them into antiparticles, then nothing happens. That's the meaning of a symmetry. Okay, now I want to see which states obey what, right? That's why I'm bothering in all these properties of this transformation. Right? It's a transformation really. I'm taking the system, I'm doing something, and I want to see if after I did something, what happens to my system. Is it still behaving the same or it is not? Now there are some very deep insights there, which I'm not sure how deep we will have time to go to in this course, but I will definitely mention it down the line some more. If I try to. Okay. Now, Similar to P, C is a multiplicative quantum number. And again, the strong and electromagnetic interactions do conserve C, but the weak interaction violates C. So that's kind of important because remember that one of the open questions that I marked at the beginning of this course is, why is the universe made of matter and not antimatter? Because, there is this complete symmetry between matter and antimatter, but still when we look around us, we are surrounded by matter, not antimatter. So there must have been something, some process that is related, that broke the symmetry. Produce much more matter than antimatter. Now, I won't go as far as telling you that I or actually anybody knows what this process is, right? But there is this process. Must have been some times in the history of the universe. It's not even sure that it was exactly the weak, because we talked about a little bit about the running coupling constants and higher energies. It might have been something else. But for right now, for the universe we live in right now, it can only be the weak. Okay. So examples, right? What is the C for photon and the pion 0? So I said that the gamma, the photon, right, is an eigenstate of C. What's the eigenvalue?
One, I think.
Yeah. Is an eigenstate of C. It's the eigenvalue of -1, of course. Why did the -1? There is a very simple intuitive way of showing that it's a -1. What is the photon associated with which field?
Electromagnetic.
Electromagnetic. What happens to the electromagnetic field when I change sign? When the electrons turn into positrons, what happens to them, to it? Right, if I have an electric field of a particle, now the particle turns into an antiparticle, what happens to the electric field?
Switches direction.
Switches direction, exactly. That's exactly what we're seeing here with the photon. I cannot do a proper derivation because then we have to take the full Lagrangian and the electromagnetic interaction part. So I just give you the simple basic argument. Okay. Electromagnetic field, change sign. Understood. What about the pion 0? So again, here pion 0, I'm going to use the observational result, which means that the most common decay channel of the pion is to 2 photons, and not, for example, to 3 photons. Now, it could have, without this charge conjugation, it could have decayed into 3 photons as well. But most of the decay, so observationally again, experimentally, more than 99% the decay channel pion 0 is pion 0 decays into 2 photons. And electromagnetic charge conserves electromagnetic interaction is conserved charge conjugation. C is conserved under electromagnetic interaction. So C of the pion 0 is just C of 2 photons. And we said that C is multiplicative. So that means that this is C of gamma times C of gamma. So this is -1 times -1, which is +1. That is exactly the reason why experimentally we never observed the decay of the pion into 3 photons. Right? So if we look at the branch ratio, PR it's called, right? Pion 0 decaying into gamma plus gamma plus gamma divided by the branching ratio of pi 0 into gamma plus gamma, then I know that it is smaller experimentally than 10 to the -8. So it never happens. Now you can see why. Because charge conjugation is not conserved, because the charge conjugation of 3 gammas is a -1. And of the pion 0, it's +1. Okay, notation is commonly used. You might have seen that if you looked already at the PDG. So the common notation for the quantum numbers of particle under the symmetries is JPC. JPC, that's what you often see. For example, right, for the pion 0, right, we know that, just a second, I finish and I'll answer. P is -1 and C is +1. And we know that J is equal to 0. So for the pion 0, we write JPC is equal to 0 -1 minus plus. Always minus, it doesn't matter, so always a 1. That's how we write it for the pion 0. You might have seen that if you looked already at the PDG. Yes, question.
Yeah, if you say that charge that C is conserved, then why is, I mean, then I would expect the pion decaying to 3 gammas to be never, not smaller than some finite number.
Yeah, you're right. That's I think this is the experimental result. I don't think it ever happens.
It's kind of the upper limit of the experiment. Like you cannot.
From where I read it, I think it's the upper limit.
Okay. Okay.
No,
but so theoretically, it never happens, right?
Yeah.
I would not include this into my Feynman diagram, whatever.
Yes.
Okay.
This is not supposed to happen. Well,
what about weak interactions?
Exactly. That is the exception. But it can happen via the weak interactions, but then again, the probability, but then again, the probability for that to happen yeah, it's much weaker. I mean, it can happen. You're right. This can happen via the weak interactions. Yeah, but it's going to be much weaker because of the difference in the masses. Because that means that it has to be mediated. You know what? It has to be mediated by the Z boson. You know what? Go and check out if it ever happened. From what I read, it did not, but possibly you could find that it did happen in any experiment, but then it can only happen via the weak interaction. Okay. Good. So let's take another question. I don't think I'm going to have time to finish everything now. But worst case, I'll just finish with that first few minutes on Thursday's lecture. So another question. Question number 2. So let's look at the state of pi plus and pi minus. So we said that the charged pion, consider pi plus plus pi minus. So a charged pion is not an eigenstate of C, but pi plus and pi minus are antiparticles. So the combined state has a Q equal to 0. Right? So these are antiparticles, so Q pi plus plus pi minus is equal to 0. So it is an eigenstate of C. So the question is, what is the eigenvalue? So again, this comes back to one of the questions that I would ask. So you can think of the two pions as having a small separation with some distance r, right? So you can think of them as pi plus, pi minus, and pi plus. What will happen? Okay. So pi minus and pi plus, right? And they have relative angular momentum L. So since this is a combination of particle and antiparticle, then the spin, combined spin, what it would be? Would be a 0. And also the total angular momentum would be 0. So in that case, acting on C, on the state, is really inverting their relative location. Do like pi minus pi plus. If I act on that with a C, then pi minus becomes a pi plus, and the pi plus becomes a pi minus. So it's really the same as if I'm acting on that with a P. Right? If I act on that with a P, I get the same result. Right? But P, right, is meaning that I take R and convert it into -1, which is what we just did. So for this particular case, we can use the properties of the parity transformation. So use the properties of the parity transformation. So C that acts on pi plus plus pi minus with some orbital angular momentum L is the same as the parity that acts on pi plus plus pi minus with an orbital angular momentum L. So this is just eta pion squared times -1 to the power L times pi plus plus pi minus L, which this is just 1. This is just -1 to the power L pi plus plus pi minus L. L is the relative angular momentum between the pions. Okay. I want to give one more example, so I'll give it now and we'll finish with this. So we won't have to proceed on that on Thursday. So another example, final one for today. I'm taking a few more minutes of your time. Hopefully it's not too much. So another question. Which of the following two processes are allowed? And the processes are the decay of the F particle into a pion and a photon, and the decay of the rho particle into a pion and a photon. And in order to answer that, I'll give you the relevant quantum numbers in the following table. So we have four particles here, F, rho, pion, and gamma. So we have the mass, units of MeV. We have the charge, and we have J, EC. So the mass of the F is 600, charge are always 0, and JPC is 0 plus plus. The rho particle is 775, charge is 0, it's a 1 minus minus. The pion is 139, no charge and 0 minus plus, and the photon has 0 mass, 0 charge, it's a 1 minus minus. So in both these processes, we have that energy, electromagnetic charge, baryon number, lepton number, everything is conserved. So there is no problem. Energy, EM charge, lepton, all conserved. These are electromagnetic decays, so P and C must be conserved. Look at the parity. So what is the parity of the final state? Parity, final state. P of photon plus pion. Right, eta photon, eta pion, and then minus 1 to the power L. So we spoke about it already. It's a minus 1 times minus 1 times minus 1 to the power L. So it's just a minus 1 to the power L. Now look at the initial state. So for the initial state, we have to look at the table, right? So P, what is P of the F particle? It's written here in the table. What is P of the F particle?
Plus?
What is P? 1, right? It's written right here. It's a plus 1. So the initial and final states are equal if L is equal to 2n, where n is an integer number, natural number. What is P of the rho 0?
Minus 1.
minus 1, right? So that means that L must be equal to 2n plus 1. So we have a constraint on L. Right, so L, in principle, we can measure L by looking at the distribution, angular distribution of the decay products. Okay, that's get us something, but that's not enough. Let's look at the C. So what is C of the final state? Charge, conjugation, final state. So C of gamma plus pion, right? C gamma times C of the pion, which is minus 1 times plus 1. So this is a minus 1. Right? What is C of the initial state? What is C of the F0?
Plus or minus.
Right? What is C?
It can be either plus or minus.
No.
It's plus. It looks like a plus minus.
Here it's a plus. Right? C of F0 is a plus 1. And what is C of the rho particle?
Minus.
It's a minus 1. So, which of the decays is allowed?
Oh,
Rho, right? So only the decay rho goes to photon plus pion 0 is allowed. Okay, I knew it's going to be somewhat longer than usual. But we have finished what I wanted to say about parity and charge, and the rest you will be given in homework. So put the exercise today before next week, next Thursday or Friday. All right. It's been a little bit technical. I don't think it's been that bad if you look at it. I tried to put it into small pieces so that you understand where it stands. And as usual, the more you practice it, then the easier it is to understand it. Questions?
I have a question.
Yeah.
We said earlier in the course that the photon doesn't have any sort of charge. And yet
It does not have the what?
the photon, we said, doesn't have any sort of charge
Correct, yes.
on itself.
Yes.
And yet it is its charge parity eigenvalue is -1.
Yes.
Is there any other, aside from its definition as the EM field, is there any other way to tell us why?
The photon, the photon does not have an electromagnetic charge, but it does have intrinsic properties. Right? We have already seen some of the intrinsic properties of the photon, right? The photon does have spin, for example, right? It doesn't have a charge, but it is an eigenstate of the charge conjugation. So don't get the name may be a little bit misleading, but maybe not, right? So even particles such as a photon, which are electromagnetically neutral, they do have intrinsic properties. Although we treat particles, in the kindergarten, right? We think of particles as being billiard balls. They actually do have intrinsic properties.
So,
we have to consider this. So the photon is one of the particles, and the photon does have various intrinsic properties of its own.
So particles that are that don't have any charge, not only EM charge, but in general, might also have a negative eigenvalue for that.
Yes, yes. I said that we have two particles, single particles that I mentioned, that are eigenstates of the charge conjugation operator C, the photon and the pion 0. But I also say that we can think of a composite system, right? So I can think of a state that composed of two particles as a single state, a particle and its own RT particle, right? And as a combined system, this also has, it is an eigenstate of C. Right? What is an eigenstate? That means that if I operate on C, I get the same particle, but multiplied by some value. In the case of a photon, it is a -1.
Mm-hmm.
Right? If I take a C and I apply it to a charged particle, for example, the pion minus, I get a pion plus. Okay.
Yes.
So it's a mathematical game that we're playing. It's not that I can take some pion minus and make it a pion plus, but I can just think of it, as some symmetry of the system,
Mm-hmm.
right? And that symmetry of the system is useful to tell me which processes can happen to the pion or the photon or the quark, or which processes happen in nature.
So there is some sort of difference between a photon and an anti-photon in its properties, sort of.
But we don't have an anti-photon, right? The photon is its own anti-photon.
Mm-hmm.
Okay.
Yes, I guess maybe I'll understand better in the next lecture if it's about the same.
I'll try to, but try to do the homework. No, it's an important point. I'm again, go back. We haven't really done properly, but actually, I don't think it's ever done properly. When I think of it, all these concepts of symmetries, right? It's a mathematical. Again, our interest in that follows from Netto's theory. That's what I said, right? If I'm able to find the symmetry of nature, then Netto's theorem tells me that there is something is conserved. And I like conserved things because that helps me determine which processes can occur in nature and which do not. Right? We love conservation of energy because that we can solve Newton's equations without conservation of energy. It's identical to do it with conservation of energy, but it gives us a much more powerful insight into the physics because it tells us which, there are a lot of processes which we can immediately exclude simply based on conservation of energy. So it's the same thing here. We have conservation of charge, we have conservation of parity. These are symmetries. So when these occur, then they automatically tell us that some processes would occur and some others would not occur.
Thank you.
Okay, do you have any further questions?
What happens if I apply charge parity to a gluon? Do I get a different color, an anti-color?
No, color is something else.
But you said that charge conservation flips all the charges.
Yeah, you get an anti-color. So you have green and an anti-green. That you can have.
Okay.
You do have 3 colors and 3 anti-colors corresponding. Okay, more? I told you the importance of parity and charge conjugate violation is one of the mysteries. Again, this is one of goes back to the question of why we are made of particles and not antiparticles. What happened somewhere in the history of universe, or maybe there is something fundamental in the physics we do not understand that cause us to be all made of matter and not antimatter. All right. So see you on Thursday. I will post today at a certain point. Worst case tomorrow if I don't have time to complete the problem set, which will be for next weekend. And then we'll proceed to discuss. We have some very nice things coming ahead. We're going to speak about the Proca equation, and then we're going to speak about the Dirac equation and see how we describe spin half particles. But then we'll discuss weak interactions, and I think we have more things to discuss than time in the semester. But I'll do my best to make it. I don't want to rush because I want it to be accessible. I can easily rush, but then the price is that I will just lose some of you, and I don't want to do that. All right.
Thank you very much.
See you around.
Thank you.
Bye-bye, and stay safe, and see you on Thursday.
אסף?
כן.
קבעת